In this video, we're going to be looking at an example of determining the amount of work required to stretch a spring a certain distance from its equilibrium position. Here we're told that a certain spring requires 100 joules of work to be stretched 0.5 meters from its equilibrium position, and we need to determine the amount of work required to stretch the spring 1.25 meters from its equilibrium position, assuming Hooke's law is obeyed. So remember that Hooke's law tells us that we have f of x equals kx, meaning that this gives the force needed to stretch our spring x units beyond its equilibrium position. So in order to answer this question, we're going to need to determine the spring constant k for this spring and then use that to answer the question about the amount of work required. So first thing we need to do is find the spring constant k. Okay, so we know we have Hooke's law with f of x equals kx. We also know that we have this equation that we're going to have to use when we're finding work to stretch our spring a certain distance. So work is equal to this integral from a to b of kx of the force function dx. And so when we look at this question of finding the spring constant k, we need to see what information we have that can help us determine k. We're told that the spring requires 100 joules of work to be stretched 0.5 meters beyond its equilibrium position. So in that case, we don't want to use this force equation because I don't have some sort of units of force to stretch the spring. What I have here is some units of work. So I need to set 100 joules equal to an integral from 0 to 0.5 of kx dx in order to determine my spring constant k. So I see I'm going to have 100 equals kx squared over 2, evaluated from 0 to 0.5, or 0 to 1/2. So we have 100 equals k over 2 times 1/2 squared, or 1/4, okay, minus 0 squared. So we see that k is going to be equal to 800. So you know that the units of this here would be newtons per meter, right? Since the force would be in units of newtons, and x would be in units, say, of meters here, then k is in this units of newtons per meter. Okay, so we've got our spring constant k. Now we need to use that to answer the question of finding the work done here. Okay, specifically we want to find the work done to stretch our spring 1.25 meters from its equilibrium position. So the amount of work is going to equal an integral from 0, which represents our equilibrium position. Remember, we've got our spring at 0. Here, in this case, I'm trying to stretch it 1.25 meters beyond the equilibrium position. So I'm going from 0 to 1.25. And I'm going to need to integrate kx here, where k is equal to 800. So I'm integrating 800x dx. Okay, so we're going to have 800 x squared over 2 from 0 to 1.25. Notice it's going to be a little easier for us arithmetic-wise here to convert the 1.25 to a fraction. So I'm going to say from 0 to 5/4 here. So I have 400 times 5/4 squared minus 0 squared. Okay, so we have 400 times 25 over 16. So we can start to simplify this here. Divide this by 4, divide this by 4, divide by 4 again, divide by 4 again. So I get 25 times 25, which gives me 625 joules for the amount of work done in this case. Okay, so things that we have to be careful of is often going to be determining which equation I need to use. Do I need to use this force equation here, or do I need to use this work equation? But those are the two main formulas that you'll be using in our different spring problems.